Hello everyone, my name is Emiting. I'm a master's student at Midwest Technical University at the Department of Chemistry. I'm working on perovskite solar cells, and mostly my study is about 3D, 2D perovskite solar cells. Today I will present my recent studies about 2D perovskite layer based on organic design for increased efficiency and stability. First article about 3D perovskite solar cells was published in 2009 with the efficiency of 3%, and this efficiency increased up to 25% in 2012 and 2019. On the other hand, for 2D perovskite solar cells, first article was made in 2014 and it increased up to 18%. And nowadays, number of publications about 2D perovskites are increasing drastically. When we talk about 3D perovskite, we are mainly focused on ABX3 structure. A represents the small organic cation, B represents the inorganic small cation, and X is the halide. For formation of 3D perovskites, the radius should be obey the tolerance factor. That means radius of the A, X, and B should obey this factor, and it should be in between 0.8 to 1 in order to form 3D perovskite. When we are talking about 2D perovskite, this time we are introducing a large cation or organic spacer into the bulk, and we are exceeding the tolerance factor for low dimensional structures. What's that organic spacer? It should be an aromatic or aliphatic material. As I said before, it's a large cation. Compared to 3D ones, it has less high structure restriction. It cuts the 3D perovskite from different directions, and it creates the weak van der Waals interactions with the X3 octahedral sheets. This prevents the penetration of water into the perovskite layer, and it blocks the ion movement into the perovskite. This A prime represents the large cation, and M represents the monovalent or divalent cation. This N here represents the thickness of an inorganic layer. When we cut layer from N equals 1, it's called as 2D perovskite. When the number of layers increases up to infinity, we are calling it as a quasi-2D perovskite. In order to create a real 3D perovskite, we need to increase layer up to infinity. Both 3D and 2D perovskites have some advantages. For 3D ones, high PC and low band gap is the main advantages. For 2D ones, high moisture resistance is the best advantage. However, both of them have some disadvantages. For 3D ones, they have limited molecule design. Also, they are really unstable toward moisture, UV light, and oxygen. On the other hand, since it has large band gap, it has narrow absorption and low charge carrier mobility, also high exciton binding energy. The motivation of 3D, 2D is to combining best parameters of both 3D and 2D to create best perovskite solar cell. There are 4 different ways to create this structure. First of all, we can only use 2D perovskites rather than 3D, or we can incorporate 2D material a little bit 2D material into the 3D bulk to form 2D 3D perovskite, or we can directly coat 2D layer on top of 3D. Also, we can passivate 3D with 2D material too. In our study, our motivation to use novel salt we are calling as TT, and it's phenotyping. This molecule is organic sulfur-based molecule. It's an aromatic ring. This is mostly used in organic solar cells, and also nowadays it's used in perovskite solar cells too as an whole transport material. It has really high charge carrier mobility. That's why it's using as whole transport material. In our study, rather than incorporate it into HDL, we are directly coded on top of 3D perovskite to increase interaction between perovskite layer and whole transport layer, and hence increase the PCE. Also, it's a really hydrophobic material. With using this, we are aiming to improve stability of perovskite. As you can see here, this is our experiment design. This is a simple illustration. After we coat perovskite, we are coating TT salt in different concentrations. Due to time limitation, I only show you our further optimization. We got highest efficiency with 2 mg per milliliter salt. As a further optimization, in order to get highest efficiency and better stability, we tried different RPMs with 2 mg per milliliter salt. This time we obtained highest average PCE with 1000 RPM. Compared to reference one, it was really high. The increase per meter was Q factor. When we compare reference one with 1000 RPM was, it increased drastically in terms of Q factor. Also, it increased a little bit JSC. Their average VOCs were the same. Also, we characterized our materials with different techniques. First of all, we look at the EQ results. When we look at EQ results, we can see that their JCs are similar to each other. These results are consistent. These results are consistent. There's a small drop in JC compared to JV. More importantly, in order to see whether we obtain 2D or not, we looked at GI-XRD results at the angle of 0.5 degree, and we didn't see any peak below 10. By the way, peak below 10 indicates the formation of a 2D layer. We didn't see any peak for 5000 RPM. However, when we look at 1000 RPM, we obtain a peak around 5 degree. This means this belongs to a 2D layer. Also, when we compare the intensity ratios with the reference one, we can see that in reference one, this ratio is lower than the others because excess PbI2 is interacting with TT, and this PbI2 ratio decreases and complete ratio is increased. For proof stability of our cells, our films, we conduct a contact angle measurement. As you can see here, when we increase the thickness of 2D layer, angle is increasing because TT makes the layer more hydrophobic. Also, we are assuming that this hydrophobicity will also increase our stability too. For the stability studies, when I first started the experiment, I used TT at 5000 RPM. That's why this stability data belongs to 5000 RPM. When we look at this data, we can see that after 25 days or 600 hours, reference device only maintained its 39% of its initial efficiency. However, for TT ones, it contained 92% of its initial efficiency. We kept these devices underdark at 15% humidity. On the other hand, we conduct another stability study with TT with 1000 RPM. This time, TT stayed stable for 1000 seconds under light. Also, we will repeat the experiment in left with 1000 RPM too. If I summarize my result, I can say that we obtained the optimum concentration with 2 mg per milliliter TT salt. As a further optimization, we tried to change spin speed of TT in order to get the best device. This time, we observed that 1000 RPM had the highest efficiency as an over 19%. Also, average efficiency was 18%. To prove formation of 2D layer, we measured GI-XRD measurements, GI-XRD, and this time we saw that with 1000 RPM we got 2D layer. Also, contact angle measurements showed us that hydrophobicity increased with the addition of 2D layer. Also, it led to increased stability. Then, with TT with 5000 RPM maintained its 92 Newton efficiency, but reference only kept its initial efficiency as 39% for 25 days. Also, we did another analysis to prove light stability of TT. This time we used TT with 1000 RPM, and we saw that around 1000 seconds it was stable under light. Thank you for your attention.
Hello everyone, welcome to my presentation. Today I'm going to talk about perovskite solar cells in a title of efficiency enhancement via efficient charge carrier transfer in a halide perovskite solar cell fabricated by polymer additives. I start my presentation with introduction of perovskite solar cell, included its properties and advantages, and the goal of our study. In experimental part, I'll talk about materials and method to fabricate our perovskite solar cells. I'll continue with characterization and charge carrier modification, and at the end, I'll go through summary and conclusion. Photovoltaics have become an essential field for basic research and technology in the recent years. The development of new materials has opened new possibilities to produce low-cost and highly efficient solar devices. Perovskite, as a new candidate in this field, displays outstanding prospects. Many research efforts have been dedicated to the study of perovskite solar cells due to their high photovoltaic performance, low cost of manufacturing, and varying of fabrication method. The higher theoretical efficiency of a solar cell under a specified light spectrum is identified to be SQ limit. SQ limit, in fact, raises the computation of the higher theoretical power conversion efficiency of a solar cell based on bandgap energy, as we can see in this figure. Perovskite solar cell with a bandgap energy of about 1.6 is expected to have the highest theoretical efficiency of 30.14%. So far, the maximum efficiency, more than 23%, is certified for perovskite solar cells. The control on electron-hole combination, morphology, crystal structure, and pinhole-free deposition of perovskite absorbers are significant for increasing photovoltaic parameters. In the different types of perovskite solar cells, the morphology of perovskite layers plays an important role for photovoltaic performance. It is shown that improving the coverage of perovskite surface rises the photocurrent of perovskite solar cell. The formation of a compact and uniform perovskite layer with large crystal size is a significant factor to get the best device performance. Because of the sensitivity of perovskite solar cell to its layer quality, it is important to control morphology during manufacturing. There are several methods to get better perovskite morphology and higher efficiency, such as solvent engineering, additives, precursor materials, substrate effects, annealing temperature, and annealing time. In our study, we focused on additives. A simple and novel strategy to significantly increase the efficiency of perovskite solar cell is to use polymer additives. Conducting polymers have been studied most intensively due to their easy synthesize, high conductivity, environmental stability, and cost effectiveness. Further improvement have been achieved by incorporation of ferroelectric polymers inspired by the promising demonstration in organic photovoltaics. In our study, polymer additives are used to change nucleation and growth of perovskite layer by retarding nucleation of perovskite grain and increasing their growth to get large grain in compact perovskite layer. Besides, polypyrrole as a conductive polymer increases current of our solar cell because of its conductive properties. On the other hand, PVDF as a ferroelectric polymer additive is expected to have double effect on perovskite solar cell. First, improving perovskite layer quality, and second, inducing driving force to charge carrier extraction because of its ferroelectric properties. As we can see here, in a typical perovskite solar cell, the perovskite layer absorber is sandwiched between electron transport layer and hole transport layer. Two-step deposition method was used to prepare perovskite layer in our study. In this table, you can see the solution and the method of each layer of our perovskite solar cell. As it can be seen, polymer additive were added in latellite layer at the first step of deposition method. All steps of fabrication were done in homemade glove box with room temperature and 28 to 35% humidity. FESM, UV-Vis, XRD, PL, EIS, and photovoltaic performance measurements were done to characterize our perovskite solar cell, and all these measurements were done in ambient atmosphere with high humidity, about 60 to 80%. Perovskite layer growth and morphology strongly depend on latellite layer. Normally, compact latellite layer without pores is not desirable because it can prevent phaser reaction with methylammonium iodide. Getting a smooth latellite layer with small nanopores helps effective methylammonium iodide diffusion and expansion, which is really required to eliminate the residual latellite and to obtain much smoother perovskite layer. ACM images recorded after latellite crystallization in the presence of different amounts of polymer additives are shown in these figures. It can be seen that the uniformity of the layer depends on the fraction of the additives. An increasing polymer additives amount to 1% in latellite layer causes more nanoporous latellite layer. This effect can be seen in both polymer, while PDF give rise to much smoother latellite layers that can be seen in this image. This figure shows the FESM images of surface morphologies of the perovskite layer. As we expected, by increasing polymer additives to 1% more compact layers with fewer voids are gained compared to perovskite layer without polymer additives. FESM images indicate that polymer additive can also oriented growth of perovskite grain, resulting in elongated crystal structure with a longer crystal size. Such morphological phenomenon is more prominent in perovskite layer prepared by 1% PVDF. Besides, SCM images show excessive amount of polymer cause perovskite crystal to precipitate and agglomerate. Therefore, unsmooth perovskite layer with more voids are gained for this perovskite layer. XRD patterns of perovskite layer can be seen in these figures. As indicated in XRD figure, a diffraction peak is indicated at 12.7 degree, corresponding to residual lead iodide that has not reacted with metal ammonium iodide. By adding 1% polymer additive in perovskite precursor solution, the amount of residual PbA2 was decreased, although polypyrrole couldn't make it zero. UVB absorption was employed to study optical properties of perovskite layers. Formation of perovskite and meso-TiO2 caused a wide range of absorption from 450 to 750 nanometer as shown in the figures. More compact and uniform perovskite layer prepared by 1% polymer led to higher light absorption of perovskite layer. The overall evaluation of UV spectra confirms that getting compact and uniform perovskite layer is critical, which can be conferred by increasing light absorption in perovskite layers. PL measurements were performed to inquire into the efficiency enhancement. Generally, the morphology of perovskite layer play a key role in the charge carrier extraction. High electron extraction originates from the uniform and compact perovskite layer, and efficient electron extraction from perovskite layer causes decreasing PL intensity. The steady-state PL spectra of perovskite layer are shown in figures A, and we can see the lowest intensity of PL for the perovskite prepared by 1% polymer additive. To better understand the photon generator carrier decay behavior, time-resolved PL decay measurements were performed as shown in figure B. As it can be seen in figures, higher quality of perovskite layer in presence of 1% polymer has shorter PL decay lifetime than the other perovskite layer. Charge carrier extraction and transfer to electron and hole transport layer could be increased by decreasing the PL decay lifetime. The charge recombination transfer rates were investigated by electrochemical impedance spectroscopy. EIS plots usually include one large non-symmetrical semicircuit at low frequency, which are attributed to recombination resistance between perovskite and electron transport layer, and a small one, which is assigned to charge carrier transfer resistance at hole transport layer. Increasing in charge carrier recombination resistance means that charge carriers cannot recombine easily and their extraction will be more efficient. Therefore, perovskite solar cell fabricated by 1% polymer has more efficient charge carrier extraction and transfer. As it can be seen in EIS figure, perovskite solar cell with 1.5% polymer has a shorter recombination resistance than the pristine one, which is in good agreement with the other results. To investigate the effect of polymer on photovoltaic performance, the photovoltaic parameters of a perovskite solar cell were examined under AM 1.5 sunlight illumination. These figures exhibit JV diagrams of a perovskite solar cells with all corresponding parameters are tabulated below. Efficiency was increased to 13.2% in presence of 1% and increased to 16.5% in presence of 1% PVDF. Based on all characterization results, it can be inferred that the enhancement of efficiency is arising from more compact perovskite layer with the higher light absorbance, efficient charge carrier extraction, and lower charge carrier recombination. Well, besides all beneficial effects of PVDF in perovskite solar cell, PVDF in perovskite layers could localize electrical field which can be induced due to its ferroelectric properties, which lead to more efficient charge transfer and extraction. Application of an external electrical field can orient dipoles within PVDF. This figure shows the power conversion efficiency of the most promising sample prepared by 1% PVDF. after positive polling can be increased by 18.6%. We note here that positive polling can only affect sample with PVDF, and the power conversion efficiency of the perovskite solar cell in the absence of PVDF decreases from 10 to 8%. It means that positive polling effect happens in perovskite layer in presence of PVDF as a photovoltaic additive. And here we can see the dipole aligned by positive polling can be reoriented by negative polling, and the JV curves can be switched back to the non-polling status. The power conversion efficiency after dipole alignment are also confirmed by PLDK lifetime measurement. This figure shows that the perovskite solar cell with 100% PVDF has a much shorter PLDK lifetime, and positive polling can reduce the PLDK lifetime. Adverse effect along with JV behavior was observed in perovskite solar cell in absence of PVDF. All these findings are also supported by EIS investigation. Positive polling leads to increased charge carrier recombination resistance with 100% PVDF. So it is clear that dipole alignment can significantly improve the power conversion efficiency of perovskite solar cell. To summary, mixed halide perovskite solar cell were fabricated with a varying weight percent of different polymer additives in lead halide layer to modify perovskite layer morphology and charge carrier transport properties. Polypyrrole and PVDF improve the perovskite layer quality by optimizing nucleation and crystal growth of perovskite, resulting in uniform layer with full coverage. In presence of 100% PVDF and polypyrrole additives, the high light absorbance, efficient electron extraction, and the lower charge carrier recombination are gained with the more continuous perovskite layer. Power conversion efficiency increased from 10 to 13 by adding polypyrrole and to 16.5 by adding PVDF in perovskite solar cell. For the perovskite solar cell, which prepared by 100% PVDF, polling investigation revealed that improved device performance is indeed correlated with the dipole field induced by PVDF, and the highest power conversion of 18.6% is obtained after positive polling. Thank you for your kind attention.
Hi all, I am Eda Alemdar Yilmaz, and today I will make a presentation with the title of Efficient Green-Blue Organic Light-Emitting Diodes based on thermally activated delayed fluorescence butterfly shape emitters. Organic light-emitting diodes emerging as the highly attractive technology for displays and future lighting. But until recently, there were only two practical emission mechanisms for these light-emitting devices, fluorescence and phosphorescence, each having trade-offs among efficiency, cost, and instability. However, things are changed at 2012 with the demonstration of thermally activated delayed fluorescence mechanism. OLED technology may usher in a new era of large area, transparent, flexible, and low energy display and lighting products. The flexibility of OLEDs enables manufacturers to produce OLEDs using roll-to-roll manufacturing process and allows for the production of flexible displays and lighting products. OLEDs are commercially produced on rigid glass substrates mainly. However, first applications like watch or band displays using flexible OLEDs have entered to the market lately. To appreciate what makes this TADF process unique, one must first understand how OLEDs produce light. When electricity is applied to an OLED, positive and negative charges are injected to a device, to the device. Before light is emitting, positive charge and a negative charge meet on a same molecule, forming an energetic state called an exciton. The electrically created excitons come in two varieties, singlets and triplets, with 25% of excitons naturally being created as singlets and 75% as triplets. When designing organic light-emitting diodes, several parameters are important to consider, and it is important to keep in mind that diverse materials as well as diverse device architectures affect the performance of the device. As general, glass is used as a substrate and indium tin oxide used as an anode. And then hole injection layer, hole transport layer, emissive layer, hole blocking layer, and electron transport layer comes. Finally, cathode layers takes place. While designing, we have to be sure that all these layers, highest occupied molecular orbital and lowest unoccupied molecular orbital levels are compatible. As I mentioned in the previous slide, generally glass and indium tin oxide is used as a substrate and anode. However, in this study, flexible polyethylene tetraphthalate and graphene was preferred. Indium tin oxide is brittle and it is not proper for flexible devices. Moreover, graphene is cheaper than the indium tin oxide. However, graphene has major trade-offs. One of them is high sheet resistance and the other one is low work function. To minimize these effects, some optimizations were done. Graphene was produced by using CVD method. Copper was used as a substrate, and after cold rolling, acid treatment was applied. Argon and hydrogen gases was used, and finally, after graft, rapid cooling were done. As you can see from the Raman spectrum, single-layer graphene was produced. At the left bottom, optical images were given before and after annealing processes. Nitric acid doping mechanism ran according to this equation. Let me explain three generations of OLEDs. The first generation OLED released only the energy and singlet of light through a process known as fluorescence. Thus, efficiency is too low, is about 25%, because 75% of the excitons did not emit light. The next generation, second generation OLEDs, was the development of emitters that efficiently produce light from triplets. The process known as phosphorescence, by including heavy metals in the molecule by also converting singlets to triplets. Phosphorescent materials can produce light from 100% of the excitons. However, heavy metal, which is often excitons, which is often a rare element such as iridium and platinum, restricts the freedom of the chemical design and increases cost. As for TADF and or third generation organic light emitting diodes, when the excitation occurs, electrons excite to the singlet excited level, and with intersystem crossing, 25% of excitons goes to the triplet excited level with intersystem crossing, and then all these excitons goes back to the singlet excited level with reverse intersystem crossing, and then they make a radiative decay. So we can get 100% internal quantum efficiency from thermally activated delayed fluorescence, and one of the most important things is thermally activated delayed fluorescence. We do not use heavy metals here, but it is so crucial in thermally activated delayed fluorescence mechanism that singlet excited level and triplet excited level should be so close to each other. It should be almost 0.1 electrovolt, between singlet excited state and triplet excited state. So molecular design is so important in this generation. Let me briefly explain the experimental part. After the etching processes, substrates were ultrasonicated with Hellman's deionized water and isopropyl alcohol for 15 minutes respectively, and oxygen plasma were applied to remove residual organic impurities to reduce the surface tension of the graphene and to increase the work function of the graphene. PEDAT-PSS were coating. PEDAT-PSS was coated by using spin coater, and all organic layers were deposited by using organic vapor phase deposition. Then substrates were taken into the metal evaporator, and measurements were taken by using Keepley source meter and integrated sphere. Under the light of these informations, we have designed a device. At the bottom, we use polyethylene tetraphthalate flexible PET as a substrate, and on the PET, we transferred 7-layer doped graphene as an anode. Then PEDAT-PSS and isopropyl alcohol mixture was used as whole injection layer, and then alpha NPD was used as whole transport layer. Host material CVP and synthesized gas material OOPCE was used in the emissive layer. Then TPBI was deposited as electron transport layer. Lithium fluoride and aluminium were deposited by using metal evaporator under the low pressure. And as you can see from the energy diagram, energy levels of the layers are so proper for electron and holes transformation. After the optimization finished, we have reached 4.3 volt turn-on voltage and almost 16,000 candela per meter square luminescence value. You can see the electroluminescence versus wavelength graph and the current efficiency versus voltage graph here. And you can see the final picture of our device when it is lighting. And you can see the chromaticity diagram. When another small molecule, decathlon type molecule, is used in the emissive layer as a guest material, we get blue color, and we get blue color with 400 candela per meter square luminescence value. You can see the electroluminescence versus wavelength graph, current density versus voltage graph, and luminescence versus voltage graph. And finally, chromaticity diagram here. You can see our device final picture here. As conclusion, highly efficient, expensive transition metal-free, PADF-based organic materials were designed and synthesized, and development of single and multi-layer graphene anodes with 30 ohm per square resistance and 80% optical transmittance on flexible substrates were succeeded. Highly luminescent TADF-based OLED devices worked with low turn-on voltage, and external quantum efficiency value was measured as 7.7%, which proves TADF mechanism. I would like to thank Professor Dr. Ali Şirpan and Professor Dr. Ahmet Oral for their support and guidance. And I would like to thank Associated Professor Dr. Görkem Gümbaş for his support and designing organic molecules. Finally, I would like to praise Sherry for her friendship, support, and graphene works during this project. And also, I would like to thank you for listening to me. Here is my references. If you have any question, I would like to answer.
Hello, everybody. I hope everyone hearing me very well. Today, I'm going to talk about production and investigation of the flexible dye-synthesized solar cells by using binder-free titanium dioxide paste as photoanode material. The outline as following: dye-synthesized solar cells, formulation of titanium dioxide paste, preparation and characterization of photoanode, platinum electrode production, and the NGB curve of our flexible dye-sensitized solar cell. Dye-sensitized solar cells have 5 components: semiconductor, sensitizer, electrolyte, electrode, mechanical part. First, semiconductor. In organic dye-based solar cells, it is necessary to use oxide semiconductors with a wide band gap to provide transparency in the visible region. Some semiconductors used in organic dye-based solar cells like titanium dioxide, zinc oxide, and tin oxide. Advantages of titanium dioxide which we use is more stable titanium dioxide iodine containing liquid electrolyte over time. And the second one, sensitizer, the task of dye is to provide electrons to the semiconductor layer to which it is bound by chemical bonds. We use as a sensitizer an 719 ruthenium dye. And the third one, electrolyte, we use as an electrolyte END. The task of electrolyte reduce the sensitizer. For electrode, it forms the positive end of the electrical circuit. We use as an electrode platinum. PT has high conductivity and excellent electrocatalytic activity. For the last one, mechanical part, for mechanical parts, we use polyethylene terephthalate. On the mechanical part, you can see here transparent conducting oxides. We use as a TCO in dim tin oxide. For production of flexible dye-sensitized solar cells, we have 2 parts. One of them here, photoelectrode production, and the second one, PT electrode production. And for 2 parts, ITO PET was used as flexible conductive substrate. First, titanium dioxide pass, which allows low temperature annealing, was produced photoanode. Produced titanium dioxide pass was sprayed on ITO PET with ductor blade and immersed to the N719 ruthenium dye. In addition, we prepared photoelectrode. And then later, platinum-plated electrode was used on ITO PET by chemical reduction method. A hole was made for electrolyte dropping. And the last step, photoanodes and counter electrodes were combined at 110 degrees, and we product flexible dye-synthesis cell. For formulation of titanium dioxide fast, first we use 1.1 gram P25 nanoparticles titanium dioxide powder. And then we add 2.5 milliliter phenol and 1.25 milliliter water. Then pH equal 4.6 HCl acid and 1.5 milliliter ethanol used. And the last step, 2-hour magnetic stirrer with it. For preparation of photoanode, the ITO substrate was cleaned using acetone and methanol in an ultrasonic bath, respectively. And this step is very important. Because of that, we couldn't clean very well that can be affected direct efficiency. Titanium dioxide pad was sprayed on the prepared ITO substrates by ductor blade method and dried at room temperature for 30 minutes. Then the flame was dried on the hot plate at 120 degrees 15 minutes and sintered at 145 degrees for 2 hours. Titanium dioxide photoelectrode surface morphology was examined by field emission scanning electron microscope. The gaps between titanium dioxide particles are caused by low temperature annealing and not using a special binder. The picture and EDS spectrum given to confirm that titanium dioxide provides good contact IoT PET surface. The gold coating may provide better conductivity. For this reason, we are seeing the peak of gold. The for XRD measurement, titanium dioxide has three different crystal structures: anatase, rutile, and perovskite. The anatase form of titanium dioxide shows the best photoactivity properties. And we know anatase form more active with low temperature. Here, it is seen that titanium dioxide pass coated on ITO pad is in anatase phase at 25, 46, and 53 degrees, and titanium dioxide pass has a good crystal phase. And after this step, we use dye. We prepare 0.5 millimolar and 719 with acetonitrate and Pvcon solution. The flexible titanium dioxide film was lowered at 80 degrees and kept in and 719 dye solution at room temperature for 48 hours. By this step, we achieve first part. Flexible PET-ITO platinum coating, PT electrode coated on PET-ITO by chemical reduction. Before this step, we again remember that the cleaning PET-ITO is very important. And we prepared after that 10 millimolar of hexachloroplatinic acid solution and again 10 millimolar of sodium borhydride solution were prepared with ethanol. Chloroplatinic acid was dropped on the substrate and heated. After the heating process, the reduction process was completed by keeping in sodium borhydride at 40 degrees for 2 hours. And we got after that same image for PET-ITO PT electrode created by chemical reduction method. There are some cracks on the surface because of coating. After this step, we combine two parts and we drop liquid electrolyte EN15. As a result, we got flexible dye synthesis and measure it. And the result saying us current density 4.5, circuit voltage 527, filling factor 46, and the efficiency 1.1. This work will be followed by more study within the near future. Before finishing my presentation, I want to thank my supervisor, Mrs. Hatice Kambur Çavuş. Thank you for your attention.
Welcome to my presentation. In this conference, I would like to present the topic of employment of body peak chromophores as the donor materials for the organic solar cells concept. Actually, we are designing and synthesizing novel materials which are generally based body peak organic molecules, and we are utilizing them if they are efficient or not, and we are looking for their efficiencies. Just a brief information about the organic solar cells. So they are third generation along with the dye-sensitized and perovskite solar cells. So they are conductive organic polymers or small molecules are used in which we have been employing the small molecules actually. And they are solution processable and they should have a cheap and low production cost compared to the first generation like silicium our silicon-based solar cells, and they are lightweight. They are working in a solid state, not a liquid state like in the dye-sensitized solar cells, and they are durable. Transparent, could be made transparent, and they could be made flexible if you just coat them on a plastic surface. So some disadvantages could be counted as they have been generally low efficiency in comparison to the first generation solar cells, and they could go into, and they could prone to photochemical degradation since the organic molecules have been used. And a record efficiency of 17.3 have been achieved in 2018, and as you imagine, it's a highly interdisciplinary concept. So people from different disciplines should work in together in order to get in order to better understand the concept. So some small information about the working principle. We have a anode hole transport layer. On top of that, we have active layer, electron transport layer, and another electrode. And the absorber part composed of the active layer, which is actually the most important part for in our perspective, because we are working at this point. We have been designing and synthesizing absorbing materials. So the absorption layer composed of generally two compounds, which are donor and acceptor, which both are organic molecules. So they form excitones upon illumination with the solar light. So they have very short lives, and we need to get we need to form electrons and a hole from the excitons efficiently, and electrons move to the acceptor domains and go into the going from the electron transport layer and then the cathode electrode. And there is a circuit, there is a connection from the anode to the cathode actually. So the holes go into opposite direction. They go into the hole transport layer anode, and we can say connecting with the electron. So the charge separation is important in here after exciton formation. So the organic solar cells with regular geometry, there's also an inverted geometry, but we are generally working with a regular geometry. It's prepared by spin coating of the PDOT-PSS layer on top of the indium tin oxide layered glass. So the glass is made conductive by indium tin oxide. And the two components, the donor and acceptor molecules, were deposited on top of the PDOT-PSS layer after like drying of the PDOT-PSS by generally the spin coating method, which we actually are using. So there's an optional annealing method for separation of the two phases and nanomorphology. To get a better nanomorphology, this step is generally done, but actually these annealing studies have been used as an optimization study. So the evaporation of the electron transport layer on top of the active layer and the counter electrode, the aluminum electrode, and solar cell have been prepared like by this way. So as I said, the non-structural morphology is critical, and actually it's difficult to control, difficult to get a better morphology. Smooth surface, favorable phase separation are important parts in this solar cell. And here is the planar heterojunction and the bulk heterojunction, which have been used in the early times, the planar, and then for the last decade, bulk heterojunction have been used. So Just small examples about body P-based donor materials. Here is a very recent very recent publication where they get a PC value, which is the efficiency value if almost 10, which is actually a great value by working with these compounds. So actually body P chromophore have been utilized in a polymer structure since, and it's a large molecule. And with this structure, which is used frequently in these solar cell structures. So the difference of this study could be counted as the acceptor materials. Two acceptor materials, C and D, have been used, and actually they gave different efficiencies. For example, if you use the ITIC2 chloride, you get a lower efficiency, but it's actually not so low, just it's also a great value. So if you look at the studies based on the body P molecules, small molecules and polymers have been used, and with small and polymers, actually there are intermediate values, high values, and there are a bit lower values. So another study with the body P with the Zissel group, actually they synthesized body P based structures, and they show the highest value they got is the 4.7 efficiency in 2012, and they see that in very small differences they could get large impact. Actually the absorption strongly in the 710 and 720 nanometers. So what we can understand here is that the amorphous surface morphology and non-macrophase separation in the unsuccessful solar cells and in the TV2, which they got the highest value, they see that there is a molecular ordering of the chromophore where the iodine atom and the fluorine atoms are actually interacting in some way. So here our early work where we studied with the body P chromophores, where we get a maximum of 150 efficiency. I'm just skipping a bit fast, and we look to chromophores, to molecules, and we see that the BH1, which is the more less dihedral angle in the mesoposition, get a higher value. You can just investigate from this citation. And here is our design, where we design and synthesize two molecules, the BOD1 and the BOD2, which the bi-thiophene units have been used as electron-rich units, and the mesoposition effect has been investigated. What is mesoposition? Mesoposition is the disposition where the body P chromophore have been substituted with this bi-thiophene or just hydrogen. Okay, and we look for compounds with near IR absorption where the solar irradiation is actually higher, and body P units were used as electron deficient structures, and PCBM and PC71BM used as acceptors. And we got the synthesis of the BOD1 with 1 to 4 steps, and actually the BOD2 we again used the 3 compound and 4 steps each. And what we get is the photophysical and electrochemical properties. Actually, you see the absorption spectrum of the two compounds. Actually, they are quite similar, but the absorption of this BOD2 compound is a bit in blue shifted, and the BOD1 is a bit red shifted, where the absorbance is around 750 nanometers. And here is the cyclic voltammetry results, where the LUMO value is important in this organic solar cells, and we get around minus 3.74 electrovolt in both actually of the solar cells, where there's an electron injection to the LUMO of this chromophore to the fluorine acceptor. And here is some photochemical characterization. Our configuration is ITO on top of that P.PSS. And we have used both 1 and or both 2 and PC71BM as an acceptor, and then later on the aluminium as a counter electrode. And here you see the first we look for the weight ratio of the body P and the acceptor ratios. 1 to 0.5, 1 to 1, and 1 to 2 donor and acceptor ratios have been applied, and we first used the chloroform as a solvent, and actually we got efficiencies around 0.4, and they are nearly the same. So we said that the weight ratio is not generally changing the efficiencies too much. And actually in the next step we look for the solvent type changing. So we changed the chloroform to the chlorobenzene, where we got the efficiency is about doubled, 0.4 to 0.7 efficiency with the both one structure. And next we look for the we look for the acceptor changing PC71BM and PC61BM to PC71BM. Again, the efficiency is about the doubled, and we got the maximum efficiency of around 1.3 efficiency with this solar cell structure. Generally, in the literature, PC71BM is working better, can be attributed to the higher absorption of this acceptor, and it has a lower LUMO value. And what we look, the next one is the both 2 molecule, which we see that it actually is not efficient. Okay, we look for different solvents, chlorobenzene, THF, chloroform, and we didn't get a result that is near to the both one. And here is the best working solar cell security intensity and the voltage graph, where you see the both one, the blue line is the PC71BM acceptor used study, where we got the highest current density, and the highest voltage we got with the black line, which is the chlorobenzene solution with PC71BM. And the theoretical investigation, and both 1 and both 2, the DFT and the TD-DFT, were used to understand the ground and excited state in collaboration with the used data from the Gazi University, and the both species retain a planar geometry, where the both actually more planar because of the mesoposition substitution in the both bond structure. And the morphology with the AFM graphs, we see that the roughness values in both 1 is better in the chlorobenzene compared to the chloroform, where you see the values 5 to 1, and 1 is the better, the lower roughness, the better the values, the better the photovoltaic characteristics. I guess this is the most important data in the organic solar cells, the nanomorphology. As you see, the smaller, the same magnification and the smaller structures have been used, and you see in the both 2 where is the coarse structure, coarse data have been seen in here. So both 1 acceptor plant films are smoother and more homogeneous in comparison to the both 2 acceptor plant. And here is our conclusion and outlook, where the novel would be small molecule based used as donor molecules, and PC71BM and PC71BM acceptor molecules have been used, and different optimizations have been performed, and increased LUMO energies may be needed, and more compatible acceptor may be needed, and this type of solar cells actually to get a higher values. Increased interaction between the body P units may be needed, so there should be some more interaction between interacting groups can be substituted to the body P units in order to, in the solid state, in order to get them have some interaction, okay, as in the Zissel example, the iodine and the fluorine examples. So other versions of body P donor chromophores in progress in our laboratory, and we are working on other type of third generation solar cells, actually the Perovskite and the dye-sensitized solar cells we have been working with in collaboration with other groups. And thank you, our grad students, Büşra and Beytullah Tatar, and the previous members, Mutayra and Gamze Dölek, and our collaborators. Thank you for them for their collaboration, the Mahmut Kush and Cisem Kırbek from Konya Technical University, which they formed the organic solar cells, which we design and synthesize, and Yavuz Dede and Derya Öncel Özgür from the Gazi University, which they performed the theoretical studies and to get better understand the structures and the morphology, and of course the Tübitak and the laboratories where we work actually. And thank you all for listening, and I'm happy to get to answer any questions.
Thank you for joining this presentation. My name is Mustafa Shah and I am from the Department of Polymer Science and Technology. So I will talk to you about our recent study which reveals the effect of functionalization of random copolymers on the performance of organic solar cells. We designed and synthesized two random copolymers. One of them has alkyl chain on the organic spacer, which is located in the polymer backbone. And at the end of this presentation, you will see how introduction of this alkyl chain affects polymer properties and device performance. Before discussing the results of the solar cell devices based on these two polymers, let's see what's an organic solar cell and how it functions. And then see what kind of polymers were used for device fabrication and why we have chosen them. An organic solar cell is a type of solar cell where the absorbing layer is based on organic semiconductors, which can be typically either polymers or small molecules. The problem of this technology is the stability and efficiency, yet research on organic solar cells is challenging and intensive since they are environmentally friendly, inexpensive, and easily processed. The first organic solar cell was reported by Tang in 1986 with a power conversion efficiency of 1%. The cell had a bilayer structure, basically a donor unit and an acceptor unit. As the donor material, he used copper phthalocyanine, which is an organic compound. And as an acceptor, he used perylene derivatives to fabricate a bilayer organic solar cell. Perylene is a polycyclic aromatic compound. Bilayer architectures result in low power conversion efficiencies. We may think that for the first study, this efficiency might be moderate, but compared to other methods, bilayer solar cells are not that efficient. Another approach for the design of the devices was proposed to increase the efficiencies. This approach is bulk heterojunction architecture, which was reported by Sarıçiftçi and Heger in 1992. Organic solar cells are generally based on bulk heterojunction architecture. It includes an active layer, which is a blend between an electron donor and an electron acceptor. The blend has a penetrating network structure due to self-organized phase separation. Compared to a simple bilayer architecture, the bulk heterojunction geometry provides a greater total surface area for charge separation and reduced recombination. These advantages result in higher power conversion efficiencies. For an organic solar cell to function, multiple steps are followed. Absorption spectrum of organic layer is very crucial for collection of light. It should match solar emission spectrum. In order to get a good matching, the band gap of the organic material can be optimized. Thickness of the layer is important here. It should be thick enough to absorb the incident light. Increasing the thickness is an advantage, of course, for the absorption of light, but this can also disturb the charge transport if it's too thick. So this animation shows how an organic solar cell functions when exposed to solar radiation. Sending photons to the active layer, an electron is removed from HOMO of the donor to the LUMO of it, and it leaves a hole behind. This hole, an electron pair, is called exciton. Then the electron is transferred to the LUMO of the acceptor. Those charges are collected at opposite electrodes, resulting in the generation of electricity. So this all was the theoretical part. Now I will show you what we are doing for this purpose. Polymer synthesis were achieved by Stille polycondensation, which is a specific coupling method between compounds with different functional groups. Following the method, polymers were chemically synthesized. Polycondensation means formation of polymers by the combination of different compounds, basically monomers. The compound you see is our core unit in the polymer backbone. So why have we chosen it? Basically, it is geometry. Simple structure of TPD is beneficial for electron delocalization. It promotes intra and interchain interactions between polymer chains, and its strong electron withdrawing ability this effect leads to low energy levels, which are desired in order to increase open circuit voltage of solar devices. Introduction of side chains on nitrogen provides investigation of the effect of side chain engineering in TPD monomers. Here a branched alkyl chain is used. Linear chains on TPD generally provide better performances in thin film transistors. The branched chains on the unit improves the compatibility of acceptor unit into the blend film, and this leads to higher efficiencies in organic solar cells. Various reports till now reveal TPD-based conjugated polymers for the application of non-fullerene organic solar cells with power conversion efficiencies exceeding from 3% to 16% with different device architectures, of course. Now let's see some chemistry. This is the synthetic pathway for the monomer and the polymers. As you can understand from the illustration, a multi-stepwise process was followed to obtain the desired polymers. Many purification steps were followed and the polymers were characterized by various spectroscopic methods for structure analysis. Here, X and Y represents the pendant groups on the organic spacer, which was introduced to enhance the optoelectronic properties of the polymers, like band gap, absorption, and charge transport. You are seeing an alkyl chain over here. This pendant group on the first polymer resulted in better performance of solar devices, which we will see later. In our study, we also investigated electronic properties of the polymers. A method called cyclic voltammetry was applied. Cyclic voltammetry is a crucial method for determination of HOMO and LUMO energy levels. Difference of these energy levels gives us electronic band gaps of the polymers. HOMO and LUMO energy levels of both polymers were calculated by using the oxidation and reduction onset values, which are determined from voltammograms. Electronic band gap of the polymer, first polymer was determined as 1.86 electron volt, and for the second polymer we found it 1.74 electron volts. Later we will compare these values with optical band gaps of the polymers. UV visible spectra of the polymer films were recorded while incrementally potentials were being applied. Then the optical band gap values of these polymers were calculated from the onset values of the neutral state absorption, and they were found as 1.78 and 1.69 electron volts. Electronic band gaps, as you might remember, were larger than optical band gaps. That is because in cyclic voltammetry method, extra electrons were injected, and when polymer films go back to their neutral state, they still carry some charges. That is the reason. Now we know conventional organic solar cells generally include a bulk heterojunction architecture. Absorption of light by this blend of semiconductors generates excitons, which are splitting into free charges. The left figure is basically the architecture of our devices. We used indium tin oxide coated glass substrate where indium tin oxide is anode. PSS is used as Hall transport layer. Onto this Hall transport layer, we spin coated active layer, which is the blend of donor and acceptor. At the top, lithium fluoride was evaporated as buffer layer and aluminum as cathode. Organic solar cells have various components, but acceptor materials significantly define the efficiency. Fullerene derivatives with astonishing features and the super ability to create fast separation in the blend led them to be utilized in the bulk heterojunction devices as promising acceptors. But there are various drawbacks, like high cost of production and purification, vulnerability to air, limited light absorption, and some difficulties that are faced in adjusting the optoelectronic properties. These aspects brought a challenge in increasing the efficiencies of organic solar cells. That is exactly why non-fullerene acceptors have caught great attention. Compared to fullerene derivatives, non-fullerene acceptor molecules can be synthesized and purified easily with various functional groups that also can adjust optoelectronic properties. And in addition to the synthesis facilities, enhanced light absorption, morphology, and electronic properties eliminate fullerene derivative acceptors. So we fabricated our devices considering all these facts. Here are solar cell parameters of our devices. The first polymer exhibited the best performance. Various polymer and acceptor ratios were prepared. We obtained the best performance with 1:1 ratio as 7.94%. For the first polymer blend, here you can see we have done chloromethylene additive treatment. This is generally supposed to enhance the device performance, but it didn't work here. So the best result was obtained without any additive. Second polymer-based devices exhibited relatively lower efficiencies. The best result was 1.96%. This is a dramatic decrease. Now I want to draw your attention to polymer synthesis section. You will remember that we were talking about alkyl chain effect on the device performance. When you look at the polymers, they are almost the same, but that pendant chain made a great contribution to the solar device. Second polymer exhibited solubility problems due to lack of alkyl chains. We want our polymers to be processed in solvents, so introduction of these kind of alkyl chains will provide a good solubility. That proves introduction of alkyl chains to the polymer's backbone enhances solubility and electronic properties. Finally, of course, solar cell performances. So in the left, you see current density voltage characteristic curves of the best results. Here it is also obvious that the first polymer-based device exhibited better performance. At the right, you see external quantum efficiency curve. The incident photon to electron conversion efficiency was studied to confirm the photo response of the best device. The highest IPCE value for polymer 1 and for polymer 2 reached 82% and 26% respectively, also shown in the figure. So the topography and morphology investigations were also performed by atomic force microscopy and transmission electron microscopy. It is obvious that the second polymer-based films have rough surface and a non-uniform coating, which can be seen also in both 2D and 3D AFM images. Here in the third image, there is also roughness, which is caused by the addition of additive. Earlier I mentioned it didn't enhance the device performance. Here you can also topographically see why this happened. TEM images were also recorded to get further ideas about morphology. Here in the first image, we can see that uniformity of the film supplements our results for the first polymer-based devices. However, in the second image, there are dark areas caused by the aggregation of acceptor, which is kind of trapped in the polymer matrix. The third image shows how addition of an additive negatively affects the device performance due to the same results. Here, the idea was to show how introduction of alkyl pendant groups, or we can say alkyl chain groups, to the polymer backbone can affect the device performance. I hope I have given an idea about how tuning chemical structures of polymers can be such effective. That, ladies and gentlemen, was all I wanted to share with you. Finally, I would like to express my gratitude and appreciation to Professor Dr. Levent Topare for giving me this chance to work with him. Also to Professor Dr. Ali Çırpan, Associate Professor Dr. Görkem Günbaş, Assistant Professor Dr. Şerife Özdemir Hacıoğlu, and Eda Alemdar Yılmaz for this study. Thank you.